Hi there, welcome to my video about molarity, osmolarity, and milliosmolarity. I'm going to start by really explaining what exactly is molarity, how does that relate to solutions, and then how does that relate to the body's ability to take on water or actually release water into solutions as we talk about osmolarity and milliosmolarity. So first, let's talk about molarity. So the molar concentration is really the relationship between the solute. The solute is any tiny, quote, cute little dissolved particles. And so when I call something a solute, what I'm really referring to are ions. They could be sodium, chloride, magnesium, potassium, whatever that looks like. Or it could be smaller molecules, such as OH, a hydroxide. Or it could be larger molecules such as glucose, fructose, types of sugars, proteins, and such. So really the solute is any dissolved compound or molecule or atom that is dissolved in a solvent. Now, solvents are usually water. So we're dealing with biological solutions. So our solvent, when we're talking about that, the main solvent is going to be water. When you dissolve the solute together with the solvent, you get the solution to the whole problem. So the solution is all of it together. So when we're talking about molarity, what we're really talking about is the concentration of the solute per the amount of water. So let's go ahead and start with some molarity problems. This isn't going straight into the molarity yet. We need to really talk about what the molar mass is first. So I gave us two examples. Example number one has A and B. So calculate the number of grams present in the following. So we're going to start. Both of these are going to use these same step values, but I decided to go ahead and separate them out so you can see the difference. So 1.25 moles of sodium fluoride, NaF. So in order to do this, first we need to calculate the molar mass, okay? The molar mass is going to be the individual mass, atomic mass of sodium plus the individual atomic mass plus fluorine. Put them together, you got the molar mass. Step number two, use that molar mass calculation, that answer, to derive a conversion factor. And that conversion factor label is grams per mole. So we're going to talk about that on the next page. So these two steps will also apply when I do the next example B. So let's start with example A. How many grams in 1.25 moles of sodium fluoride? So your step one, here's what I did. I got the atomic mass for sodium, 2.99. You will find this on your periodic table. Fluorine, 19.00. Notice I rounded them to the 2 decimal places. If you will see, there's actually more decimal places, but it rounds. Add them together, the atomic mass for sodium, the atomic mass for fluorine, put them together. That is the molar mass for the entire ionic compound. So the molar mass of sodium fluoride is 41.99, but you have to understand the association. Grams of sodium fluoride per 1 mole of sodium fluoride. There is an equivalent of this being the molar mass is going to be equivalent to 1 mole of it. And the reason why we do this is when you're in the lab, you measure out grams. You put it on the electronic balance and you measure it out. And then you mix it with the solvent so you can make your solution. We don't measure out moles. Moles is going to be an equivalency to how many molecules in that actual subset of concentration of that solute, I should say. So with that, we went over in Bio 111 how 1 mole has an equivalency to that Avogadro's number in molecules. We're not going to be covering this in this video. Go ahead and find another video if you need a refresher on that, but we won't be using that. So the next step, we're going to go ahead and take this molar mass, and we are going to calculate how many grams. So the question is, what do we know? We know we have 1.25 moles. That's what we want, is 1.25 moles. we need to figure out how many grams are we going to measure out in order to do that. So we get started with what we know first, 1.25 moles of NaF. And then we take our conversion factor. I know it's a big, scary word. It just means that these are equivalent. It could be in this position or it can be flipped around. Luckily, we're put in this position. Why? Because moles is on top here, and we need to get rid of that unit's moles. So that's why we put it on the bottom. So from there, we just calculate. We cancel out the moles. We cancel out the moles. We're left with the label of grams. We multiply 1.25 times 41.99. That's where we get 52.49 grams of sodium fluoride. That's how we know what to measure out. So let's do the next problem. So the question is, how many grams of 3.5 moles in C2H6? I specifically chose this. This is going to be a hydrocarbon because it has more than one atom of carbon. It's got 2 atoms of carbon. And this has 6 atoms of hydrogen. So we need to account for every single atomic mass of every single atom. So let's look over here. Carbon, the atomic mass of carbon is 12.01. You get that from your periodic table. Because there are 2 atoms of it, we're going to times that by 2, getting 24.04. Hydrogen, the atomic mass of hydrogen is 1.01. We have 6 atoms of hydrogen, times it by 6. So you have 6.06. Add these together, your total is going to be 30.10. And the labels for that, so your molar mass of C2H6 is 30.10 grams. And we always put the label C2H6 per 1 mole of C2H6. Now that we have built this conversion factor, we're going to use it to calculate how many grams in 3.5 moles. So we get started with what we know, 3.5 moles of C2H6. We use the conversion factor. We put the moles piece on the bottom. The 1 always goes with the moles, by the way. And then we're going to cancel out the moles label, cancel out the moles label. We're left with the grams label. 3.5 times 30.10 is going to be 105.35 grams of C2H6. Notice how I boxed my final answer. That will be the expectation as I'm grading your work. All right, so let's do another example. We're going to go ahead and hit the problem from another angle. So the next set of questions, next question is calculate the number of moles. Last time I was asking for grams. Now I'm asking for the number of moles in 250 milliliter solution of 1.5 molar solution total, okay, of MgBr2. And so what that means is this is the liquid portion. This right here is the molarity portion that includes both the solvent and the solute. Okay, so we have a nice little calculation that we're going to keep referring back to, this little formula. And I would put this formula in your top paper to see if it's needed. It's not always needed. As you can see in the last 2 examples, I didn't need this formula, but a lot of times it is needed. So molarity. Molarity is denoted as big M. A lot of times people get that confused and put a little m. Little m refers to meters, okay? And I believe it also refers to molality too. So you got to make sure you're putting the correct units label, which is capital M. Moles of solute. Moles of solute is usually just spelled out moles, or sometimes they get lazy and leave off the S and just call it mole. But it's very different than molarity. And liters of solution. So your liters of solution, just straight liters, metric system. So here's our steps. I put our steps out. Number 1, we're going to use this molarity formula. Number 1, to identify, what do I know? Okay, I know some things over here in the problem. And the next question, what do I need to find out? Well, it's asking me here, find out the number of moles. So step number 2, because I've been given milliliters and this is in liters, we need to convert milliliters into liters. Then from there, we just use this formula and we start plugging and chugging. So let's go ahead and get started. So the first thing I'm going to do in step 1, what do I know? I know I have molarity, big M molarity. I have 1.5 molarity of MgBr. And I know milliliters, okay? Well, now that we know milliliters, step 2 is to convert that 250 milliliters into liters. So what do? We set it up where we can cancel out milliliters. We're left with the liters label. 250 divided by 1,000 is 0.025 liters. All right, so our next thing, step 3, as I say, plug and chug. So I brought our molarity formula back again so we can see that. We're going to have to do a little bit of manipulation here because you can't just make labels go away. You have to be able to cancel labels out. So looking at this, big M equals moles per liter, as you can see that. Well, I put this here in red. If I said big M equals moles per liter, then I could take this moles per liter and put it over here and replace big M. Because like I say here, it's the same thing. Now I've manipulated what I have, and I'm going to use this on the next page. So I have, don't look at the purple sides. Let's look in the middle, the black box. 1.5 moles per liter, I pulled that from the last page, equals the amount of moles of that solute over the amount of liters. We calculated it was 0.25 liters of solution. Okay, so the goal is we need to isolate moles by itself because the question is to solve for moles. So in order to isolate moles by itself, we need to get rid of this liters piece on the bottom. You need to go back into your algebra. Your algebra to get this isolated, we are going to times this side of the equal sign by 0.25 liter solution. Now we can cancel that and cancel that. But whatever we do to this side of the equal sign, we have to do to this side of the equal sign. So if we times 0.25 on this side of the equal sign, we have to do it on this side also. But look at that. Now we're only going to cancel liters and we cancel liter label. We leave the number, okay? We have isolated moles on this side. You can see I put my work down here. Now we are left with 0.25. We times it by 1.5 moles, and that's what the label of moles of MgBr2 is. 0.25 times 1.5 equals 0.38 moles of MgBr2. Notice I boxed my answer. Hopefully I did all my basic math right. So feel free to check me, let me know. Alrighty, so that's how you do that when you're solving for moles, when you are given molarity and milliliters. All right, let's go ahead and go to another example. In this example, they're asking you to calculate molarity, big M, okay? This is the easiest of them all, I'm going to tell you. So here, once again, we're using our formula. So we need to look at it. Our step 1, what do we know? What do we need to find out? Well, we don't know big M. That's what we need to find out. We do know milliliters. So like before, we're going to need to, step number 2, convert milliliters into liters. And then we can check off this piece, okay? But here's the deal. We don't know grams. So as much as I said this is the easiest, it's not too bad. It is. So we are going to find moles with grams. And how do we do that? Like our first example I gave you, you are going to use that molar mass conversion in order to do that. So we need to figure out the molar mass. Then step number 4, plug and chug. So let's go ahead and get moving. So first of all, to calculate that molarity, let's, like I said, figure out, we know grams, we know milliliters. Let's go ahead and convert milliliters into liters. Boom. You already know how to do that, so let's follow to the next. Then we need to calculate the molar mass for KBr. So individually, The atomic mass of potassium, looking at the periodic table, is 39.10. The atomic mass of bromine, looking at the periodic table, is 79.9. I had to round up, okay? So I always round up to 2 decimals. You never want to round up to the first decimal. You want to save some room here because sometimes that does make a difference. Sometimes it doesn't. Okay, so let's add them together. Your molar mass for KBr is 119.00. I kept those 2 decimal places because they are significant at this point. So 119.00 grams of potassium bromide per 1 mole of potassium bromide. You're starting to see the similarity from every single one. And so from there, we're going to take this conversion factor. We know grams, 36 grams of potassium bromide, right? So that's what we know. So that's what we put here always, because that's what we get started with. 36 grams. We use this conversion factor. We put the grams on the bottom. Ooh, that's different. We had to flip this conversion factor in order to get the label of grams to be where we canceled. So only the conversion factor is flippable. Never force this on the bottom because this is what we are starting with. This is what we know and we're working with in the lab. It's always the conversion factor that can be flippable. So always keep the number value with the grams also. Don't try to put this 119 up here. So let's go ahead and get started. 119 grams of potassium bromide per 1 mole of potassium bromide. We can now cancel out grams and potassium bromide, grams potassium bromide. We're left with mole, and that's good because that's what we're going to need for the next stage. So 36 times 1 divided by 119 is 0.3 moles potassium bromide. But that's not my final answer. That's going to take us to the next stage. Our next step is to use our molarity formula. So now we have everything we need. We have, from the previous step, 0.3 moles of potassium bromide. That's the solute. Remember, the solute is always the tiny dissolved cute particles. And 0.2 liters of solution. We got this from step 2 a couple of slides ago. Looks like I decided to keep 2 equal signs in this. No worries, I'll take it out when I give you your final version. So divide this by this, and now you have big M, your molarity, 1.5 molarity potassium bromide. Notice how I speak. I say molarity, and this is moles. They're not the same thing. So make sure you're using not only the correct units, you know, when you're putting it through your mind and you're talking it through, make sure you're using the correct words because they are not equivalent. Alrighty, so this right here, 1.5 molarity of potassium bromide. We're going to use this in a later example. Let's move on to the concept of osmolarity and milliosmolarity. So in a body system, we've talked about this in 111. If you've had me, if you haven't, you probably have talked about it in your previous 111. In your body system, your cells have the ability to take on water or release water. And it all has to do with the solution in which they are dissolved in or immersed in. Okay, so put a nice little definition of what osmolarity is. Osmolarity is going to be the molar concentration of dissolved particles per 1 liter solution. That sounds very generic. Don't worry, we are going to apply it. But before we move on, let's just go ahead and give you this formula because it's pretty simple. 1 osmolarity, this is how you make it shorter. Make sure you put a space in there. That way it doesn't look like you're giving me the number 10. Okay, I purposely put a huge space in there. So you can see 1 osmolarity is equivalent to 1,000 milliosmolarity, just like a regular metric system. Shouldn't be a problem. Okay, so before we move on to some examples, I'm going to do a quick review of tonicity. And so first, where tonicity is always dealing with the solution in which the cell is compared to. So here's my cell floating in solution. I put the cell in a beaker. but you could put this red blood cell inside a bloodstream. So apply it that way. You're going to have a lot of that application in your anatomy and physiology. So right here, I'm showing you an isotonic solution. Remember, we're talking about the solution in which the cell is being compared to. So why is this an isotonic solution? Well, first of all, let's count how many solutes in the cell. 1, 2, 3, 4, 5, 6. 6 solutes in the cell. We plop that cell into the solution, and luckily it's an isotonic solution because there's 1, 2, 3, 4, 5, 6. There's 6 solutes in the solution. So this solution is isotonic it's isotonic solution to that cell. All right, let's move it on. How about this one? This one is a hypertonic solution. So the cell that I immersed it in, I only gave it 3 solutes, but we plopped it in a solution that has, 3 times as much, 4 times as much, a lot more. We're going to call this a hypertonic solution because it has more tonicity, more solutes compared to that cell that is being compared to it. So this is hypertonic. Because of that solution and the hypertonicity, these solutes have a great pulling power on the water inside the cell. So if you recall, the water inside the cell will leave and come out here to try to establish water equilibrium, okay? So these solutes will essentially pull on water and make that cell shrink. Moving on to this one. All righty. This cell has a lot of solutes inside, and you plop it into a solution that's hypotonic. Hypotonic, lower solute concentration. Well, kind of the same thing, because if you recall your osmosis, water wants to move from a high water concentration towards a lower water concentration across a selectively permeable membrane. So water is going to go from the solution into the cell because these solutes have a greater pulling power to try to draw in water. So with that, this cell is going to gain lots of water and could eventually probably will burst. It will swell and swell and swell and take on water until it bursts or reaches equilibrium. It really depends on that tonicity of that hypotonic solution. So let's go ahead and apply this now to different types of compounds, okay? I use the word compound because molecules are not, if you recall from your 111, a molecule really has to do with a compound that is in a fixed ratio, like specifically your water, H2O, in a fixed ratio. It's got 2 hydrogens and 2 oxygens. But we can very well call this organic compounds versus ionic compounds. So that is the word I'm going to be using in this discussion. So all of your molecules, all of your, just kidding, all of your compounds do not have the same affinity to draw water in or out of a cell, okay? And the reason why, your organic compounds do not disassociate their atoms when you dissolve them in a solution. Each of their molecules are going to remain as one particle. I can call it a molecule because it's organic. They're going to remain in one particle. Guess which ones these are? Your carbon-based compounds. And your carbon-based compounds, if you recall, they are your covalent bonders. So they're not going to disassociate because those covalent bonds are very strong. Versus ionic compounds. Ionic compounds do disassociate, which are break apart when you dissolve them in water. Those are your ionic bonders. For example, your sodium chloride. So I'm going to give you these examples on the next page. So 3 examples I'm giving you is going to be glucose, sodium chloride, and magnesium chloride. So glucose is C6H12O6. So because this is an ionic, because this is a covalent compound, okay, it is not going to dissociate when it goes into the solution. And it's going to be considered one particle. Let's look at that. Boom. All right, I'm going to back it up. This one here, sodium chloride, is going to dissociate and break up. The sodium and the chloride are going to become ions. This is going to become a cation. This is going to become an anion. And thereby, they break apart, making two particles in the solution. Then you have your magnesium chloride. One magnesium, the purple I denoted, and two chlorine, the green. So that is going to end up dissociating into the ions, your cation and two anions, and making three particles. So now let me show you what this does for the ability of the solution. If you just kind of recall back in our tonicity, and we're going to apply this. So your glucose just goes in as one particle. So what if I were to put 4 glucose molecules in? Let's count them up. 1, 2, 3, 4. Those 4 glucose molecules don't dissociate, thereby only make 4 particles of solute into that solution. Okay, so that essentially is only going to make, you know what? I don't think I want to go there yet. Let's save it. Let's go to the next. All righty, sodium chloride. Here's your sodium, here's your chloride. When you put them into the water, it's going to make a sodium chloride solution. But the sodium and the chloride dissociate into their ions, their cation and their anion, and look at that. Wow, you have so much more. You have double the amount because it makes 2 particles. So if I were to put in 4 sodium chloride compounds, that is going to make 8 particles of solute, right? This would have been one of them, 2, 3, and 4. But because they break apart, this essentially makes 8 particles of solution. So this is going to have a greater affinity to pull on water. And so this is going to make a solution be more hypertonic when compared to looking at this solution. All right, so let's go to the next one, and that's going to be magnesium chloride. So magnesium chloride is going to break into 3 particles. The reason why is 1 magnesium, 2 chlorine, boom, 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 you throw them in when you break apart. So if I were to, in the same, throw in 4 magnesium chloride compounds, that is going to dissociate into 12 solutes, right? 1, 2, 3, 4. I'll let you count them up. So this has a greater affinity to draw on water than if you were to put in sodium chloride, than if you were to compare it to glucose. So this is definitely going to make more of a hypertonic solution. So the big take home for this is it does matter what compound is going into a solution. So let's go ahead and do a couple of example problems. So we're going to calculate the osmolarity of 3.5 molarity of sucrose. And I just gave you, this is the molecular formula for sucrose solution. Okay, so the step one, determine how many particles are going to dissociate it. Well, this is a carbon-based compound, right? It's organic. So that means even though it has all of these atoms, it is not going to dissociate. So it's only going to make 1 particle. And the second step is to multiply the molarity by the number of particles. We already gave it away. It only has 1 particle, like I said. Sucrose, carbon-based compound, does not dissociate into the individual carbons, hydrogens, and oxygen atoms. It remains as 1 particle. Step number 2, multiply the molarity by the 1 particle. You're like, okay, so now that we have this information, let's just go ahead and take our previous 3.5 molarity sucrose. We want to figure out what is the osmolarity. What's its ability to pull on water in a biological medium, i.e. your body. So 3.5 molarity of sucrose solution times one particle, because we've denoted only one particle, is going to be equivalent to 3.5 osmolarity of sucrose. So they're equivalent. You're going to find the same thing with glucose. You're going to find the same thing with fructose. So yeah, I think I just gave away a bunch of your answers. Let's try a different example. So I'm going to take the answer from our example 3 a few slides back. Remember, our example 3 asked to calculate the number of molarity for 36 grams of KBr in 200 milliliters of solution. This was our final answer, 1.5 molarity of KBr. Why would I do another problem when I can just continue the last one? All right, so let's go ahead and take this right here and figure out, now we need to calculate the osmolarity of that 1.5 molarities of potassium bromide. So for step 1, determine how many particles it's going to dissociate into. Step 2, multiply the molarity by the number of particles. Pretty easy. Let's go to it. So step 1, potassium bromide, it's ionic. So that means it is going to dissociate into its cation of potassium and the anion of bromine. So thereby, it's going to make 2 particles. So step number 2, multiply the molarity by the number of particles. Well, the molarity that I gave you was 1.5 molarity of KBr, times that by 2 particles, and your answer is 3.0 osmolarity of KBr. Don't forget to box your answer. All right, so let's go to the next. What do you say we figure out, take this, now let's calculate the milliosmolarity. If you recall, I gave you a conversion factor when we first got started with this. It was 1 osmolarity is equivalent to 1,000 milliosmolarities. So let's take our previous answer of 3.0 osmolarities, use our conversion factor. 1,000 milliosmolarities is equivalent to 1 osmolarity. Cancel out the label osmolarity, cancel out that label osmolarity, and then we have 3 times 1,000 is equivalent to 3,000 milliosmolarities of potassium bromide. Why would I need to do this? Well, in the medical field, we're really dealing with milliosmolarities per liter. And so knowing how to calculate to this level is definitely needed. So, alrighty, so expectations. As you can see, I typed everything out. I don't expect you to type everything out. This took me almost 2 days to make this PowerPoint for you. So anyway, just you can hand do your work, but legibly show your work. Always put your compound name labels. You notice I always put C6H12O6. Actually, I didn't use a glucose. Yeah, I did. I always put KBr. Always put your name labels, because without the label, it means nothing. It could be anything. So there will be points taken off. So always put the units label. Obviously, if you're coming down the units of osmolarity, I need to know that. I need to know whether it's molarity, osmolarity, or milliosmolarity, or grams. So without the units label, it means nothing. So you also need to box your final answers, because I can't search around for everything. You need to tell me what you're giving me as your final answer. If you don't box your final answer, I'm not going to give you very much credit for the work, because I'm not going to search around for your final answer. In your D2L, I will let you know specifically how many points I will take off for these. And so it could get significant if you do not make sure you have all this. So as difficult as all of this sounds, it's actually pretty fun. The difficulty was in making the PowerPoint, not in doing the actual work itself. And so you might actually start to enjoy it.